Hi there, welcome to Geometric Series. I guess you think you know a bit about this because it's the same idea, series, as you did with arithmetic. So it means the sum of terms in a series. So if we had a series, I don't know, what's the series going on here where we're dividing this square up into smaller and smaller pieces? What is it? A half plus a quarter plus an eighth, something like that. Through there, what would be the sum of that series? That's what we're going to work on now. If there's a geometric relationship, so R here is a half, check it out, R is a half, the ratio there. So if that's the situation, can we get a formula for adding them all up? What about this one here, bouncing ball? We sort of spread it out a bit. The ball is really bouncing up and down in the one spot. But what is the total distance travelled there? Total distance moved by the ball, so it's the sum of all these. And if they were connected by a geometric relationship, then that would constitute a geometric series. Maybe the height at the beginning is 2 metres, and then it only bounces up, what's this, looks like about 3/4. So if we multiply it by 3/4, we get 3/2 or 1.5 metres. Get the idea? And then if it only keeps bouncing up by 3/4 of the height, it would be 9/8 metres, and we could get the total distance that it travels up and down by adding those terms of a geometric sequence. So that's called a geometric series when we have the plus in between. Same idea. So sum of is implied or implies you're going to look at a series of terms. All right, let's come down and have a look. These screen clippings here are from Pearson's textbook for the new IB course, standard level, first examined in 2014. So let's come down and have a look at what they say here. A geometric series is the same as with an arithmetic series. We might be wanting to sum some of the terms. A partial sum means we're thinking about the series as being infinite, and it's geometric, and we want to sum some of the terms. So here we are. Here's an example here. There we think this is going to be infinite. Keep going there, and quite clearly here the R is 2. So find the partial sum for the first 20 terms. It means add up the first 20 terms. So if we write them down, very similar to what Gauss did with the arithmetic case, 20, sum the first 20, then multiply each of those by 2. What do you notice? Well, if we multiply by R here, then that becomes that term. And so if you line them up, then these are all in common and disappear. But there's still, if S20 take 2S20, that's neg 1 lot of S20, you get 3 and this term here. So S20 is that value there. They've left a bit of a step out here. You'd actually want to say neg 3,145,728 plus 3, because that's a positive 3. So that comes to neg 3,145,725, and that's what neg S20 is. Therefore S20 is 3,145,725. That's how they've done it. So here's the trick. Use R times the first series there, and then every other term lines up and disappears. These go to 0. Can we extend that to the general case? You know, where we have just R as the ratio, not a particular one here. Let's come down and see if we can do that now. So here it is. Let's go through this carefully. So here we've got a geometric sequence terms called A1, and the ratio is 1. It's not a ratio is R. It's not equal to 1. So here's what we've got, a sequence of terms there. It's a series because we're adding them up. Then we're going to multiply each of those terms by R. So A1 becomes RA1, A2 becomes RA2, etc. And AN take 1 becomes R times AN take 1. Well, what have we actually done? Well, they're trying to put it down here that if you multiply A1 by R, you get that. And what's the definition of R times A1? That's A2. R times A2, that must be A3. Remembering in A's now, any term is R times the preceding term. Or in IB notation, it's like this. So, what have we actually got? Let's write it down now. Sn was A1 plus A2 plus A3 up to AN take 1 plus AN. But when you multiply it by R, let's have a look now. If you multiply it by R, we've got A2. Let's line them up. A1 becomes A2 plus A3, and AN take 1 is going to become AN, and then you'll have on the end RAN. They've all been displaced, haven't they? Multiply by R and it becomes the next term, so AN take 1 becomes AN. Let's now subtract it like Pearson's are saying there. So SN take RSN, so let's put that down. Now, these all go out here. All go out, but the A1 doesn't. And then it's minus, what's left here? AN goes out with that, and all the ones in between go out with the preceding ones, but it's going to be, this one's left, take RAN. Oh, it's getting a bit messy here. So let's do some factorising. Let's take Sn out, 1 take R, and then here A1 take RAN. Okay, so we have got a formula here. Sn is A1 take R times the nth term divided by 1 take R. That's a little bit messy. So could we actually do something with that? I think Pearson's are doing it down here. I'll keep going with mine over here. This is A1. Now what's the formula for the nth term? That's A1 R to the n take 1 over 1 take R. So what have we got then? We've got A1 take A1, now R times R to the n take 1. Adding of powers would be R to the n over 1 take R. Or here, A1 factored out the front, 1 take R to the n on 1 take R. So that's our formula to go straight to the sum of n terms. All you need to know is the first term, the ratio, and how many terms you want to add up. Okay, so that's an interesting formula there, and that's how we derive it. Similar to the Gauss approach, lining terms up and taking them away. You've just got a couple, this one in the front here and this one on the end that don't match. All the others subtract from each other. All right, well that derivation is not really needed as part of this course. It's interesting maths. What we need to do is to know the formula. So come down here and here's our formal statement. And of course this is the one from the IB booklet with mu's in it. Can we have a look at the two forms? We've just derived this one, and that's if R, this is a handy one, if R is less than 1 if it's a fraction, because the bottom becomes 1 take the fraction and that stays positive. This is more useful if r is greater than 1. Let's have a look at the connection between the two. We derived this one, and so let's multiply top and bottom by -1 in this one. So this becomes mu1, and this will be -1 plus r to the n, multiplying through by -1, multiply the bottom through by -1, then just putting it in a different order, we've got r to the n take 1 over r take 1, which is this one over here. So they are equivalent. One is multiplied by a negative top and bottom to get the other. So it doesn't matter which one you use. Both will give you the same answer. It's just a little bit more convenient to keep the bottom line here positive. So you'll use this one over here for r bigger than 1, and then this one when you have a fraction to keep the bottom line here positive. 1 take a fraction will give a positive. But it doesn't matter. Both will give the same answer for any r. That's what's creating negatives, that's all. Same answer for any r. Okay. So let's see if we can use it now, because that's a handy tool. Looks complicated, but once you stick numbers in place of the letters there, it comes out pretty well. Okay, let's look at a couple of examples here. Example 1, find the partial sum. Remember, partial, we're considering that this is infinite, and we're just going to add up the first 20 terms. Okay, so this was a series that we did back in the beginning of geometric sequences. So what are we going to do now? They haven't actually shown this in detail, so let's write down the formula. We'll use mu1 r to the n take 1 over r take 1. Using that one because r here is 2. So r take 1 would best be 2 take 1, not 1 take r. They've done it the other way. So we want S20. So mu1 was 3. R is 2 to the 20. Take 1 over 2 take 1. See the advantage of this formula where r is bigger than 1? We don't have to remember that negative. Okay, so we don't have negatives floating around. And therefore this is 3 by 2 to the 20 take 1, because the bottom line is just 1, and that comes to this number here. Okay. So I think it's worthwhile trying to use this formula for r bigger than 1 to avoid any negatives floating here. Okay, but this one works as well. Either formula, remember, work for any r's. They are the same formula, because if you multiply top and bottom of the fraction in one formula by -1, you will get the other formula. Okay, let's come down and look at a bit of advancement on that idea. We've got here an infinite geometric series. Okay, so it's going to keep going. But we're going to take a particular case here. We're going to take a case where r is a fraction. R is between 0 and 1. So it's halving. You see what's happening. R is a half, R is a half, all the way there. What's going to happen to this series for a large number of terms? So let's do some calculation for 10, 20 and 100 terms. So here we're using the formula, and this time they have used this other formula. See in the bottom line? If r is a fraction, 1 take r is better because it comes out to be plus a half. You don't have any negatives there. So if you sub that in and use the calculator for bigger and bigger numbers of terms, look at what's happening. Well, you can see that the terms are getting smaller and smaller here, aren't they? Smaller and smaller. And so as you take a larger number of terms, so as n tends to infinity, the sum tends to some limit, because the contribution of the terms with a bigger and bigger n is getting smaller and smaller. It looks like it's tending to the sum of 4 there, very close to 4. So let's look at Pearson's conclusion. As the number of terms increases, the partial sum appears to be approaching 4. There is no coincidence, because if we look at the language of limits, let's look at the form. We haven't done that. Maybe just pause and come back up here. This notation, remember, says that sum from k is 1 to 10 of the terms of the form 2 by half to the k take 1. That's our formula for our geometric series here. And we know that's geometric, so we've then used 2 times the sum of 10 terms. So that's 2 times A1, or I'd prefer to use mu here, mu1, 1 take r to the n over 1 take r. That's what we're doing. 2 times the sum. All right, so here it is down here, the notation. Again, what is the limit as n tends to infinity? Does this tend to some limiting value? Let's see if we can work it out. Well, look at this. A half to the k. If k tends to infinity, and we're seeing it here, right, sum from 1 to an infinite number, what's a half to an infinite number? Well, it's going to disappear, isn't it? Here it is here. The limit as n tends to infinity of a half to the n. Half to the n is going to tend to 0. Therefore, we're going to get 1 take 0 on a half, which is 2, times 2 is 4. So what is the underlying idea? If you have an r, which is a fraction, so let's put this down, it's a fraction, as the number of terms become infinite, the size of the term, mu n, will tend to 0. Therefore, the sum of the terms is going to, well, let's put it as tending to, it's going to tend to mu1 by 1 over 1 take r. Why? Because this little fella here is going to tend to 0. Okay, so, and therefore the mu n is going to get smaller and smaller. So it's going to tend to 1 in that bracket. 1 take r to the n will tend to, this bracket will tend to 1, because r to the n will tend to 0. A fraction raised to a bigger and bigger power will tend to disappear, will tend to 0. So that's the idea. Let's have a look at what's the statement here in the in Pearson's, also from the information booklet for the IB. So here, let's not worry about the derivation, we've done that, but here is the formula we usually use. And what we're saying here is r to the n will tend to 0 as the number of the term gets bigger. You've raised a fraction to a bigger and bigger power, and therefore you talk about the sum is the limit of that. As n tends to infinity, what's that going to do? If we take an infinite number of terms, not a partial sum, an infinite number of terms. And so it's going to tend to mu1 over 1 take r. So this is called the sum of an infinite geometric series. You can only use this idea of limits if n is tending to infinity, not if you're taking just a partial sum for the first 20 or 30. You use the same formula, here it is here. I prefer this is what's in the information booklet. So we use S infinity. What's that? S infinity. So that means you're taking an infinite number of n values, bigger and bigger n, and if you raise a fraction, here it is, that's another way of putting it, the size of r, the modulus or absolute value of the ratio, absolute value of r is less than 1. That means whenever r is a fraction, you're going to get this petering out, this reducing of the size of the term, because remember, r to the n will tend to 0, okay, as n tends to infinity. And that's our idea. Okay, so let's go and do some problems now. Here's a couple of examples. Let's do example 18. A rational number is a number that can be expressed as a quotient of two integers. Don't like quotient, rational, ratio of two integers. Okay, ratio now, number. It's a ratio. I prefer a ratio of two integers. A quotient, it means the same thing, two things divided. So show that this is a rational number. Well, the decimal keeps going, so it doesn't look as if it is, but it's repeating. Do you realise that if it was just 0.689, that's clearly rational. If that stops, that's equal to 689 over 1,000. So that is a ratio of integers. It's only the 0.6 recurring that's a bit of a headache. But you can think of 0.6 recurring as 0.6 and then plus a 0.06, plus a 0.006, etc. Looking at it from a series point of view. There is another way of looking at 0.6 recurring, but we'll just take it this way for a start. So what is that? That's 6 tenths plus 6 tenths by a tenth plus 6 tenths by a tenth squared, etc. So it is actually geometric with mu1 6 tenths, and all the other decimals that keep recurring are 1/10 of the previous one. So therefore, what are we doing? We're summing an infinite number of terms, so it's mu1 over 1 take r, so it equals 6 tenths over 1 take r is 1 take 1/10, which is 6 tenths over 9 tenths. Division by a fraction, you invert and multiply. I hope you can explain why that works, inverting and multiplying. So it comes to 6/9 or 2/3. So it is a ratio of integers, even though it doesn't seem so, 0.66666. So that's an interesting way of looking at a recurring decimal, and we're going to practice that a bit later on, looking at it as a series, a sum of these decimals here, getting smaller and smaller. All right, let's have a look at example 19. I put this up at the introduction, of course. So here we have a ball that has elasticity. It bounces up 80% of its previous height. Find the total distances travelled. Ignore friction and air resistance. So here we're going to start with an altitude of 3 metres. Now obviously this diagram isn't correct. Usually the ball would in fact be bouncing up and down in the one spot and get smaller and smaller. So we've spread it out, spread the motion out for clarity, spread the motion out to actually see the distances more clearly. But it would be the ball bouncing up and down the one spot. Okay, so what have we got? 80%, so it bounces 3 metres high for a start. Then 80% is, what can you do that? Is 4/5, okay, or 2.4, and another 80%, etc. So can you see that that is a series? Let's go here. 3 metres plus, then it was 2.4 plus 1.92 plus, and it keeps going. So what is the ratio here? We're multiplying by 0.80 each time. 0.80, a fraction. So it's going to gradually tend to 0, these terms. So the sum will be, let's have a look. Over here, it's 3. Now, we must double the sum here because it bounces up and back. Okay, to the same point. So it's not quite as easy as what I've got here, because it bounces 3 metres and then when it comes down it only bounces 2.4. So from here onwards you have to multiply it by 2. Goes up and then it bounces again. So can you get that idea here? What we would then do is in this bracket, this is going to be infinite. It's going to keep going. So can we use our formula, our sum for an infinite number is equal to mu1 over 1 take r. Now the actual first term here that is doubled is not the 3. That's the first bounce. It only goes up once. They're talking it here. The ball is dropped, sorry, the initial 3 metres, so that's being dropped, so that's only coming down here. So it shouldn't have that arrow there. It's being dropped down 3 metres, so we're not going to double that. It's not a double bounce there. But the rest of these will be. So here, what we've got is the sum of those in brackets there will be the first bounce, okay, over 1 take 0.8, and if you work that 2.4 over 0.2, or 2.4 over a fifth, is 2.4 times 5 over 1, which is 12. So all those bouncings in here, forever, infinite, comes to 12 metres. But they go up and come down again, so we're going to double it. So the ball is dropped 3 metres, and then we've got the doubling of the infinite number of bounces. It gradually peters out to nothing. So the sum of our infinite series is the total distance that ball travels is 27 metres. So that's an interesting problem. Okay, just note here that the ball is being dropped here. So it doesn't go up and down that 3 metres twice. Okay, so let's go down and have a look at some problems. Now, Pearson's haven't got many problems here. I have actually separated from the previous arithmetic series presentation the question 1 and 3, which was arithmetic, and these are the only ones in Pearson's textbook that relate to geometric series. So I've put those here. You can pause the presentation and go down and have a look at the solutions I'm going to show you. But I've also added some other problems for a bit more practice here. So let's go down and have a look at the solutions. So there's question 2 and 4, 5, 6 is coming up. Question 3 was arithmetic, so that was in the last presentation. So you can pause your work and check it there. And then if we go to 6, I think we can fit 6 on there. Question 6, check that out. Then question 7. Okay. So that's the end of those. Now come down with me for some more problems, because I've taken some screen clippings here from another publisher, Hayes and Harris, and have a few more questions there for us. So here, if we wanted to find the formula for the sum of n terms and just keep it to n, keep the n in there, don't say when it's going to stop, then here what have we got? We've got an r of neg1/3, so they've got an interesting one in there. Alternating sign, r is neg1/3 timesing by neg1/3. So there's our formula. We use that one because r is a fraction. Okay, so let's go back up. We lost that then. Okay, so r is a fraction. And so putting the numbers in, first term is 9, 1 take, and it's neg1/3 to the n. Be careful. If r has a negative, all of it is raised to the power. And that will give you alternating signs up here, won't it? Alternating signs, because a negative raised to an odd power is a negative odd raised to an even power is a positive. So every other time you multiply by a negative, you're going to get a positive, and so on. So we have a look here. This answer cannot be simplified, as we do not know if n is odd or even. So that's our final answer there. Now that's a good tool. If we wanted to find S10, just put 10 in place of n. Okay, come down now and let's do some. So find the sum of the following series. A bit more practice here, and I think you do need practice of actually, this is various n's are given. Here they just want you to put the general Sn. In other words, it'll end up with a formula in n will still be there. Evaluate these geometric series. Do you understand the sigma? So write out the series using the idea of that sigma notation. It tells you when to start and when to finish. Okay, so start writing those terms out, and then once you got the hang of it, sum them up. Just check that they are geometric. Okay, and then in question 4 now, just coming down to question 4. Each year a salesperson is paid a bonus, so let's have a look at the series involved there. And here's a little entry problem that I had up there to introduce series. So have a look at that and try to relate it to the diagram. That's interesting. And then some solutions there. Okay. So rewind the presentation and have a go at those. I've got some more for you. Come down. Here's a few more. There's infinite series, and that's a rational number problem again. Same idea as with Pearson's, and some more here. You might not do all those. We've had some of those. And as you go through, this is looking at the infinite series one now, using this formula. They might actually put S infinity there more correctly. Okay, S infinity meaning the sum of an infinite series, and you can only do this if the size of R is less than 1. That is, it's a fraction. R is between 0 and 1. That's the only time you can talk about an infinite sum, because that's the only time the actual terms peter out into nothing and you approach a limiting value for the sum. Okay, so as you go through, have a look at those. Oh, here's the ball problem again. But this time it's a little bit different. Hey, we'll do this one because it's 90% of a bounce. And it's talking about the time taken now. The time taken, not the distance. So that's not a bad one. Okay, and here's the point I made before. The diagram is inaccurate as the motion is really up and down on the same spot, being separated out to help us visualise what's happening. All right, so we've seen a couple of those now. Okay, so pause the presentation as you go and have a look. And then here are the answers. Okay, so I'll take you back now up to the problems here and have a look. All right, so that's the end of geometric series. I hope you're happy with the skills you're building up. You might go back and check some of the ideas because we're coming to the end now of sequences and series, and all I've got for you left in the final presentation there is some practice questions from Pearson's. I think there's about 63 of them with fully worked solutions, so we'll get onto those in the next presentation. But for now, cheers from me.